I'm happy to be here to present this work. We enable low-cost touch tracking for paper. We call this method, first of all, my name is Zhang. We call this method Pulp Nonfiction. This work has been done with my advisor, Chris. So despite the ubiquity of digital devices such as phones and tablets, people still use quite a lot of papers. Since paper is versatile, tangible, and readily accessible, it is used in a wide array of products, from newspapers, calendars, board games, food packaging, to cups and Post-it notes. We present a low-cost touch sensing approach for paper. Our approach tracks fingers as well as writing implements. So importantly, the cost of our approach is so low that a user can simply throw away after a single use, which we believe is one of the key reasons why paper is still successful. Of course, there have been many previous approaches aiming to make paper an input surface. We can use external sensors to augment papers. For example, previous work used cameras, usually set above the desk to track papers, as well as fingers. It is also possible to use cameras in mobile and wearable platforms such as these digital pens, rings, and also our smartphones. Finally, previous systems also used underlying digitizers, so it is more like papers on a smart sensing pad. More similar to our techniques are previous systems that directly instrument the paper. For example, we found previous work on flexible input surfaces really relevant to our topic. These systems have leveraged capacitive sensing and piezoelectric materials to detect touch. There have also been research attaching capacitive sensors such as copper patches to make paper touch sensitive. And finally, previous work also used conductive ink, which is very flexible and can be used to implement traces, RFID tags, and even displays on paper. So now let me talk about our sensing principle. Most related to our technique is electric field tomography, which was first studied in Smith-Caesar's work and recently demonstrated in our previous systems, TOMO and electric. Here is an illustration of our sensing principle. So the black rectangle is a layer of mildly conductive material, and the yellow dots are peripheral electrodes. So we first insert a small current using one pair of adjacent electrodes. This creates a small electric field distributed inside that conductive layer. So to measure how this electric field is distributed, we can measure voltages from all other adjacent pairs. Of course, we can improve the resolution by rotating these emitting and receiving pairs, which eventually give us this mesh of measurements. The sensing layer can be coated underneath the paper, so when the finger touches on the paper, it draws a current from the underlying electric field, which intersects with the mesh and affects the measured voltages. With this data, we can reconstruct a 2D image of the electric field distribution, which we can use to track finger. As we can see here, the red color indicates the low current density area. Here is a video of our reconstruction. Note that we can track finger positions as well as estimate the touch force. Even multi-finger is possible with sufficient separation. Let's talk about how we made this. Here you can see our sensing circuit. I will only quickly walk you through this, so I only highlight interesting parts. First, we have a Cortex M4 microcontroller with built-in ADCs. Next is the signal generator chip, which generates the excitation signal. Then we use 4 multiplexers to multiplex the excitation and ADC channels. The board then sends all the data points to a laptop, which runs machine learning to detect touch. Here are more specifications. We use 200 kilohertz 6-volt peak-to-peak excitation signal. The received signal is then measured at 4 megahertz sampling rate. We collect 200 samples for each RMS calculation. Eventually, this gives us a frame rate of roughly 35. That's for the configuration with 16 electrodes. After this project, we have been working on optimizing the circuit in terms of like price and also the sensing resolution, and eventually we cut the price down to roughly $10 per board. To explore electric field tomography on paper, we created many prototypes, testing papers with different compositions, thicknesses, and also writing implements and conductive materials. First, we wanted to identify a good paper to develop our approach on. To do this, we measured the shunting current of a finger on 10 common paper products, from 13.5 pound art paper to 129 pound cardstock. As we can see on this plot, shunting current decreases linearly with paper thickness. And we selected 16 pound printer paper, which is readily available, resulting in roughly 3 microamps of the shunting current and costs under 1 cent per paper sheet. To enable shunting, the tip of our implement must be electrically connected to a user's hand. This is just like how passive touchscreen stylus works. Some existing writing implements, such as the metal fountain pen, work immediately without modification. Others require light instrumentation. For example, the calligraphy brush on the right, we attach the copper tape running down to the brush tip. We run a similar test as before, but this time measuring the shunting current on the 16-pound printer paper, and found some small differences. However, even the smallest shunting current from the graphite pencil is still measurable. However, overall, our approach should work with a wide range of writing implements. After we investigated paper stock and writing implements, we then look at the conductive materials to implement the sensing layer. Like paper, this has to be very cheap and also flexible. We identified 2 materials that are well suited to our sensing technique. The first one is conductive plastic film, which can be laminated to the back of the paper. A second option is a carbon-loaded conductive paint, which can be brushed or spray painted. We then investigated tracing implement methods that allows our sensor board to interface our augmented paper sheets. Our first prototype, as is shown here, used hand-soldered electrodes and wires, but this worked fine, but as you can see, it's not compatible with industrial processes. So we turned to well-established printing processes such as silk screening. We also explored subtractive processes. We used a laser cutter for this prototype, but it should be equivalent to die cutting. We also created this prototype using etched copper traces, which worked the best, and so we select this one for evaluation. Now let's talk about how our touch tracking pipeline. Our sensor board first collects raw measurements from peripheral electrodes. The RMS are calculated and sent to a laptop. We use these data as features and also added statistical features such as average, mean, max, standard deviation. Finally, we also calculate the reconstructed image and add that to the feature pool. We selected the most powerful 200 features to move on to the next stage. In this stage, we first use a binary classifier to detect touch. If the data is the touch data, it is then fed to a discrete touch classifier and label the data to the closest pre-trained location, enabling button-like interactions. This touch data is also fed into 2 regression models to output continuous touch location. So these 2 outputs, both discrete and continuous, are then fed to the application layer. We run an evaluation to investigate how our technique works. We selected 3 common sizes: sticky notes, US letter, and easel, as is shown here. We built 1 finite element model for each paper and marked them with crosshairs, which we later asked participants to touch. To better tease out the performance of our technique, we also marked the paper with 5 shapes, which we later asked participants to trace. For all 3 paper sizes, we asked participants to test with both finger and a graphite pencil, which gives us a 3x2 study, 3 paper sizes and 2 writing implements. We invited 11 participants. Note that the machine learning models were pre-trained before the evaluation, which should better reflect a real-world usage. Paper should be pre-trained before it is bought by consumers. So all data recorded here are live. In total, there were 4 rounds of touch and 3 rounds of trace shapes, resulting in over 7,000 of no-touch, 5,000 of touch, and roughly 1,000 of trace shape trials. For time constraint, I will go through this very quickly, but please refer to the paper for more details. In average, our technique achieved the touch and no-touch segmentation accuracy of 97.2%. If we classify touch points to the discrete crosshairs, the accuracy was 94.1%. For continuous tracking, our technique achieved a finger tracking error of 1.4 centimeters and a pen tracking error of 4.3 centimeters. Specifically, in discrete touch location, we found pencil conditions performed worse than finger conditions. This is because pencils in general have less contact area than fingers and thus have less shunting current and less SNR. For continuous touch tracking, we found that paper size is also a significant factor that affects the tracking accuracies. The accuracy uniformly decreases with the paper size. We overlapped all drawn traces from our participants with no post-hoc modification. Here are the results when we asked participants to use their fingers to draw on the paper. We can clearly recognize the shape no matter what is the size of the paper. Here are the results for the pencil tracking. As expected, it was more challenging to track pencils than fingers, so you can see these traces are more noisy than before. These results suggest a better pen implementation and also a sensor with higher sensitivity. To inspire ideas from other people, we built a variety of example applications. For example, we can make interactive book or quizzes. The answer from students can be digitized and revealed for real-time feedback. We can also make digital sticky notes, which automatically track a user's hand drawing before it is peeled off. It is also possible to make touch-sensitive newspapers, where a user can set bookmarks or post on social networks through touch interaction. And finally, we can make interactive board games to help children learn rules, or make it more interesting through sound effect. In this example, the game senses the location of the token and provides sound effect accordingly. I want to conclude my talk with some limitations of our technique, which we believe still requires quite amount of effort to overcome before our technique can be commercially available. First, I want to talk about the cost. So although we lowered the cost by 2 orders of magnitude, so right now it costs only 30 cents per sheet in our technique, but it's still not enough for paper products. We hope to work with commercial partners to further reduce the cost through more comprehensive material exploration and also better application methods. Palm rejection is also challenging for our technique in its current state. However, we believe this is possible because we saw palm and pen tip and finger, they appear very differently in the reconstructed image. But of course, more investigation is needed in future. And finally, environment noise, such as polyline noise and fluorescent sparkles, and also grounding conditions might also affect our technique. As mentioned before, we are currently optimizing the sensor board and hope to mitigate this problem with better analog front end. That was my talk. Thank you. I'm happy to take questions.
Raimund Axelt, Interactive Media Lab Dresden. Very nice work, great work. And it's just maybe a question and a hint, two things together. First question, so did you think about eliminating this laptop display and just integrate feedback directly into the paper?
That's a good question. So in this demo, all these laptops are only for feedback so that the audience might know what is going on. But in reality, it might not be needed there. So for example, the last example, when people play board games, the sound effect can be played by a cheap microphone, just like a seeing, happy birthday card you send to other people. There could be a cheap microphone there to provide feedback. And also there are all other kind of like feedback mechanisms. You can use your phone, you can use a tablet to work together with this touch-sensitive paper. It doesn't have to be a laptop.
So and just a second is a hint. So last year at CHI we presented Illumi paper, so where we have a glowing paper, so it's integrated feedback, and you also have touch with that. So maybe you might look at this work again.
Yes, I'm a big fan of that project. Yeah.
Then cite it too.
I said it.
Rolf Vertigal, Human Media Lab, Queen's University. Excellent work. We've been in this space for a long time, and doing things like touch tape, for example, but never got the idea of doing the tomography, which is really nice. One question I have is for flexible displays, touchscreens are still challenging because they break. But the problem is you got an electronic backplane that's flexible, but it does have like electricity on it, and that might mask out some of the stuff you're doing. Have you considered integrated this somehow with a flexible screen? Either as a backplane, which probably is impossible, or as a front plane where you use some kind of, ITO or something like that. I don't know.
So let me make sure I understand your question correctly. You're asking if we considered combining this with kind of like flexible touchscreen technology together to make a better paper.
Well, no, I'm saying this could potentially be flexible touchscreen technology, but the problem is the connectivity and the shielding issues.
Yes. Actually, we never thought about that because the sole purpose of this product is to try to make really low-cost interactive papers. But I think if we want to make really cheap, soft, like flexible touchscreen, more works need to be done in terms of like a material, because I need materials that are also conductive, but both conductive and also transparent to make screens, right? Rather than paper, because paper doesn't have to be transparent. We can simply choose whatever is cheapest possible, but also like conductive. That's why I use the carbon loaded conductive paint.
Well, one option might be graphene because it's actually transparent.
Yes, that's a good idea.